In this video, we're going to work our way towards discovering a second part of the fundamental theorem of calculus, which deals with taking the derivative of an integral. Now, let's look here at this first problem here on the left-hand side, where basically we want to use the fundamental theorem of calculus we're going to rewrite this integral that goes from 2 to x of g prime of t dt. And we're going to use the evaluation part of the fundamental theorem of calculus. Well, we would start by first finding the antiderivative of g prime, which would just be g of t. And then we would go from 2 to x. Now we'd put in our upper limit, we'd have g of x minus g of 2. Now we want to turn around and we want to take the derivative of that expression, which is right here on the right hand side. So basically we want to turn around and take the derivative with respect to x for what we just did, because we just did this inside. So of g of x minus g of 2. Well, the derivative of g of x would be g prime of x. The derivative of g of 2 is just going to be 0 because that's just a constant. And so we wind up getting just g prime of x. Now, if you look at what you have here, when I took the derivative with respect to x of this integral, what happened is basically when I had this upper limit of integration being the same variable that I'm taking the derivative to, we wound up getting just what was in the integrand here, this function that we were integrating. And that is what the second fundamental theorem of calculus tells us, is that if we have a function that is continuous on an open interval containing a, then for every x inside of the interval, the derivative with respect to x of this function that is defined as the integral from a to x for f of t dt is simply the integrand, where basically it's the same function, but the inside variable went from being a t to the x because of we were turning around and taking the derivative of this antiderivative, which takes us back to what we originally started with. Now let's look at this graphically with Desmos. And so we'll start here with just some polynomial that I have graphed. And what we're going to do is we're going to graph a function that is defined as the integral from 0 to x for this f of x function, this cubic function. And I'm going to plot it here as well, and it's going to be in blue. And so we see what the antiderivative would be. Now, the fundamental theorem of calculus says that if I was able to find the antiderivative equation, which is being graphed in blue, and then I turn around and took the derivative of this antiderivative, it should wind up taking me right back to my original orange curve, which I'm going to graph now the derivative of my antiderivative function in blue, in green, and we see how the two graphs line up exactly on top of one another, which is what the second part of this fundamental theorem of calculus tells us, is that the derivative of an integral with respect to the upper bound equals the integrand. So basically, derivatives and integrals, they undo each other. So let's look at some applications here for this second part of the fundamental theorem of calculus. And we'll start right over here with this problem where let's find the derivative of g if g is defined as the integral from -2 to x for f of t dt. Well, simply the derivative of g with respect to x would equal, basically, I would just take this upper limit of integration because it's just x, and it's what I'm taking the derivative with respect to, and it would replace the t, and we wind up with just f of x. Now let's look at this when I actually have an expression inside of here for the integrand. So I want to take the derivative with respect to x of the function defined as the integral from 3 to x for f of t cubed minus 4t plus 1. So if I'm taking the derivative, see, derivatives and integrals, they undo each other in terms of their functions or their operations per se. And so what I'm going to do, if I was to integrate this and then turn around and take its derivative, basically this function is going to wind up replacing all of the variables that we have. And so we would wind up with our derivative just being 5x to the third power minus 4x plus 1. which takes us here to this next part. What if I'm taking the derivative of an integral that has functions of x's and it just doesn't have an x and a constant here? Well, to discover this, what we're going to do is we're going to do the inside here. And so if I first found the antiderivative of h, that would just, or h prime, excuse me, that would just give me h of t. And then we want to evaluate that from g of x to f of x, which simply would be h of f of x minus h of g of x. So that is what the inside is. Now we want to turn around and want to take the derivative of that expression there. So the derivative with respect to x of h of f of x minus h of g of x. To see what that equals, well, we have to do the chain rule because we have composition of functions. So basically we would have h prime of f of x times f prime of x minus h prime of g of x times g prime of x. And that's what we would get after we took the derivative of that function that we had initially had. Now let's compare what it was we had with how it is different from what we were doing. So when I take the derivative with respect to x of an integral, and I have functions of x in here, basically what happened is, previously we just had plain old x, and we would just, when we took the derivative, we put the x in for all of the variables. But since we have a function of x where it's the derivative of what I'm plugging in this case is not just 1, I have to account for doing the chain rule. So basically we would put in our upper limit first, so it'd be h prime of f of x, and then multiply by the derivative of f of x. And that's what we have here. Now, since we had another function here in the denominator, we'd have to do minus, put g in for t, that makes h prime of g of x, and then times by the derivative of that lower limit, g prime of x. Which we can extend our second part of the fundamental theorem of calculus into a definition where if I'm taking the derivative and I have functions of x's as my lower and upper limits of integration for this function, the way this would play out, which is exactly what we derived there without actually having to first find an antiderivative and then turn around and differentiate. So let's look here and let's do this problem here on the left-hand side. So I'm going to take the derivative of the function defined as the integral from x squared to 2x for f of t dt. Well, without finding the antiderivative, plugging in and turn around taking the derivative, we're just going to use this second part of the fundamental theorem of calculus, which says that we're going to take this upper limit and we're going to put it in for t, so it'd become f of 2x. And then we're going to multiply by the derivative of what we put in because of the chain rule part, so it'd be times 2. Minus, because we have a function of x in the denominator as well, it's going to go inside. So it'd be f of x squared times by the derivative of x squared, which would just be 2 times x. And that would be our answer there. Okay, another one, same thing. Let's find the derivative of g when g is defined as the integral from 6x to 4x squared of the square root of 1 plus t to the 4th power dt. Well, I'm taking the derivative of this integral, so basically g prime of x is going to equal, you start with the upper limit. I put the upper limit in for t, and so we'd have the square root of 1 plus, and then it would be 4x squared being raised to the 4th power, times by the derivative of what we put in, so times 8x, minus the square root of, now I put in the bottom limit, or the lower limit, so 1 plus, and I would have 6x being raised to the 4th power, times by the derivative of 6x, which is just 6. That's what my derivative would be. All right, so now that we can take the derivative of an integral function, let's learn what it means to define a function as an integral in terms of how to find its values. So here on the left-hand side, we'd have a graph of w of t, and g of x is defined as the definite integral from -2 to x for w of t dt. And we want to find three values here. Let's find the value of g of 0. So g of 0 is going to equal, I'm going to replace all x's with zeros. And so we'd be looking at the definite integral from -2 to 0 for w of t dt. And so we would go get that area up underneath that curve by using some form of a geometry formula to help us out to get our answers. And so we go back and we look in here on our graph and we try to get the area between the curve and the x-axis. The area from -2 to -1 is 0.5, and the area between the curve and the x-axis from -1 to 0 is 0.5. So to find the overall area, or the signed area between the curve from -2 to 0, we'd have to look at this in two parts. We'd have to find the signed area under the curve between -2 and -1. But because it's beneath the x-axis, I have to make that negative. And so that first signed area would be -0.5, and then plus the second piece from -1 to 0 is +0.5, and so that definite integral would give me 0. So g of 0 is equal to 0. Okay, well next we want to find g of 2. So basically I'd go into my g of x expression, replace all the x's with 2's, and we would get g of 2 would equal the definite integral from -2 to 2 of w of t dt. And because we're having to find the areas up underneath the curves, we don't actually have the equation. We could take the signed area, the value of the definite integral, from -2 to 0 and add whatever additional signed area we can get to go from 0 to 2 to help us get our answers. Well, we know that the overall area from -2 to 0 ended up being 0. And so simply we just need to figure out, well, what's the area up underneath the curve from 0 to 2? And so we use geometry to get this area. So from 0 to 2, we have the area of the rectangle here, base times height, which gives us 2. The area of the triangle here on the top, we get an area of 1. We put that together, we get an overall area here for 3 to go from 0 to 2. And so we put that in, and we wind up getting g of 2 is equaling to a value of 3. Okay, so next one, we want to find the value of g of -3. Well, we go back, we put in -3 for all of the x's. G of -3 would equal the definite integral from -2 to -3 for w of t dt. First thing that we notice is that the bounds need to be switched because I need to have the smaller x value on the bottom and the biggest x value or on the top, or in this case we're talking about t value. So I need to do a bound switch. And so recall, when you do a bound switch, so if I got to flip my bounds, I have, according to our properties of integrals, we got to make the integral negative. Now we can go to our graph and we can find the area up underneath the curve from -3 to -2 and then make it produce the correct sign. So we'll have -1 times, and then we need to go get our area. And so the area here is going to wind up being 1.5. We have a trapezoid, and the trapezoid formula, h over 2 times base 1 plus base 2. One base is 2, one base is 1, and so we wind up getting 3/2 or 1.5. Now when we take that back to our definite integral, because it lies beneath the x-axis, and our definite integral would produce a negative value. So we have -1 times the -1.5, and we can get the value of g of -3, just going to be positive 1.5. Okay, so now that we know how to take the derivative of a function defined as an integral, and we know how to evaluate and get values for functions defined as integrals, let's perform an analysis of a function defined as an integral. So we're given here on the left-hand side that g of x is defined as the integral from -1 to x for f of t dt, and the graph of f of t is given on the right-hand side. We want to begin by completing the table where we have some values of x that we want to find the corresponding g of x value. So what I would do first is, looking at the table, is I would start by finding g of -1. The reason why I would find g of -1 is because g of -1 would be equal to the value of the definite integral from -1 to -1 for f of t dt. Well, we know that if I'm evaluating a definite integral and the lower limit of integration is equal to the upper limit of integration, this value is going to equal 0. So I know that value there is 0. Now I would work my way from here to go get other values. Now something I can do if I had a lot of these to do, which we kind of do, is I'm going to take my graph over here on the right hand side, and I'm going to make individual areas where I'm looking in every one unit I'm going to have to compute a new value for G. So I'm going to put individual areas for every one unit that I can do on my graph to help us do this. Okay, so we go through and we get the individual areas, and this will help speed up our process a little bit. So we're getting just the areas up underneath the curve in the x-axis, and we kind of fill our way in all the way down and using the correct geometric formulas to do this. So we have all triangles and then 2 trapezoids here as we get towards the very end of the graph. All right, so let's start by finding the corresponding outputs for G at -2 and -3. So we would go into our function G that's defined as the integral. We're going to put in the corresponding x value. So we'd put in -2 for x, -3 for x, and we would rewrite what we have. So G of -2 is equal to the definite integral from -1 to -2 for f of t dt. And I did the same thing for -3. Now, one thing that we notice is that we need to do a bound switch in both of these cases. So if I have to switch my bounds, and I need to make them negative. We do the bound switch because we would like to have the smaller number as the lower limit of integration, the larger number as the upper limit of integration. So from here now what you do is you go into your graph, and we're going to use the areas up underneath the curve, and we're going to use the correct signs to get our answers. So G of -2 is going to equal to -1 times the area up underneath the curve from -1 to -2. Well, it is +1 for the area, but since it lies beneath the x-axis, we have to make it negative, and so we get a overall value of +1. Now we're going to do the same thing here. We're going to look at the overall area from -3 to -1. And so as we go from -3 to -1 here, I got this initial negative sign here. So it'd be -1 times. We have this first piece that is that's +1. It lies above the x-axis, so we have 1 plus. And then once we get the 2, we go from 2 to -1. This is beneath the x-axis, so we'd have to make it negative, so 1 plus -1. And we wind up getting a value here of 0. So G of -3 is 0. G of -2 is +1. And then we're going to work and go find the next 4 values. All right, well, now let's go find G of 0. We're going to put in 0 for the x's into our function defined as an integral. And so we wind up, G of 0 is going to equal the definite integral from -1 to 0 for the f of t dt. And we look at our graph, we see that from -1 to 0 right here, we wind up getting an area up underneath the curve of 1, but it lies beneath the x-axis, so that would be -1. And then we want to progress forward. Well, what we can do for our next one, since we want to find the value of G of 1, is the overall value for G of 1 is going to equal the overall area, signed area beneath the curve, or between the curve and the x-axis from -1 to +1. We can break this up, and we kind of been doing that a little bit already, but we're actually going to show it here. Is I can take the value that we just got from -1 to 0 for f of t dt. And we're going to add to that the value that goes from 0 to 1 for the f of t dt function. And we can go back to our graph and go get those 2 values. So we're actually writing our 2 properties of here. To go from -1 to 0, we get -1. And then to go from 0 to 1, we get -0.5. And so we get an overall value here of -1.5. Now, something else that I want to do here is I want you to look at what we have written. So G of 0 is equal to the definite integral from -1 to 0. So the definite integral from -1 to 0 of f of t dt. We actually could write G of 1 a little bit differently. We could say G of 1 is equal to G of 0 plus what we had left over here, which was the net change from 0 to 1 for f of t dt, which is a much easier way to write that instead of having to recompute all of these areas every single time. So if I take that approach, and we want to go to find the value of g of 2. G of 2 would equal my value of g at 1. So g of 1 plus the overall net change, which is the definite integral from 1 to 2 for f of t dt. Well, we know that g of 1 is negative 1.5 plus, to go find the overall net change from 1 to 2, we'd go to our graph, and from 1 to 2, the definite integral would be negative 1.5 because that lies beneath the x-axis, so we'd say plus negative 1.5, which is going to give us negative 3. And so if I continue that approach, g of 3 would equal the value at g of 2 plus the net change from 2 to 3 for f of t dt. And so g of 2 is negative 3 plus the net change would be the value of our definite integral from 2 to 3, which would be negative 2.5. And so the value of g of 3 here would be negative 5.5. All right, now let's look at doing an analysis for the function of g. And so we start, well, where is g going to be increasing or decreasing? And well, we have to go back to our derivative chapter here. So a function is going to be increasing or decreasing where we look at what its derivative is doing. So if I want to know where g is increasing, I need to first find the derivative of g and then start looking at the signs of my derivative. So g prime of x is going to equal the derivative with respect to x of, we go look at how g is defined. Well, g is defined as the integral from negative 1 to x of f of t dt. Well, here's that second part of the fundamental theorem of calculus here. So I want to take the derivative of that. So g prime of x is simply going to equal f of x. And so we can determine where g will be increasing or decreasing by looking at the sign. So g is going to be increasing. So g is going to be increasing where g prime of x is going to be greater than 0, well, which is also going to be because g prime is equal to f of x, where the f function is going to be greater than 0 or positive. So we can get that off our graph. So everywhere that the f function is positive, which is basically on this graph, it's only positive from negative 3 to negative 2. So g will be decreasing where its derivative is less than 0, or where, in this case, it's g prime of x is equal to f of x, where f of x is less than 0. And so we go to our graph here and we look, all right, well, this would be from negative 2. We'd have negative 2 to 0 and 0 to 3. Now, here's the interesting part about 0 here. It doesn't actually, at 0, pass through and start back increasing where I get a positive sign. Now, I also know from here that since we're talking about a function, that in order for us to look at if a function is increasing or decreasing, a singular one point where we equal 0 and don't actually change from increasing to decreasing, so I don't have a sign change, I'm not going to break my interval off here. Just like for the graph, if I had the graph of x cubed that looks like this, at that one brief instant for the point of inflection, we get a derivative equaling 0, but at that one point, however, the x to the third power is always increasing on its domain, and we have a similar scenario here. So actually, we would go from negative 2, because I don't actually start increasing anywhere, from negative 2 to 3, this graph is beneath the x-axis or equal to 0. And so basically it's not positive. So we're going to call it decreasing. So we're going to say it's decreasing from negative 2 to 3. And if we wanted to, in this case, I could even include the endpoint of 3 here because of the fact that it is still beneath the x-axis. And I could have actually included the endpoint on the other one as well. And so if I wanted here, we could go back and change these intervals to go inclusive on the negative 3 and inclusive on the positive 3. from my increasing and decreasing. Now, while we're here and we're looking at this for the signs of our derivatives, let's determine where we have a relative maximum or minimum. So we're going to have a relative max or min based on where we have a sign change in our first derivative. Well, we have a sign change in our first derivative looking at our intervals at -2, because our first derivative of g is equal to f of x. We change signs at -2, where I go from being above the x-axis to below the x-axis, which means at x is equal to -2, we should have a max for g, a relative max for the g function. So we have a relative max at x is equal to -2 because since we have f of x is equal to the derivative of g, and f of x changes from positive to negative at x is equal to -2, that indicates that we have a relative max, because g will go from increasing to decreasing at x is equal to -2. All right, so next one, what are the intervals where g is concave up or down? Well, concavity deals with the sign of my second derivative. The second derivative of g is actually going to equal the first derivative of f because of the way we have this function defined as an integral. And since g prime was equal to f of x, that we have here for what we just did, the second derivative of g will be equal to f prime of x. Now we need to know what we're looking at in terms of concavity. So we'll start indicating this by, okay, where would g be concave down? Well, g is going to be concave down where the sign of its second derivative is negative. Well, since we're given the graph of f, we'd have to relate this to what the sign of f prime would be. Well, f prime is the slope of f. So we're looking for where f is decreasing. So g is going to be concave down where f is decreasing at. And so we'd go look at that on our graph and say, all right, well, everywhere that f has negative slope, so from -3 to -1, from 0 to 3, it has negative slope. And so we would write those two intervals for where it's concave down based on the slope of f. Now we want to go look and see where g is concave up. It's going to be concave up where the sign of the second derivative of g is greater than 0. But since we're looking at the graph of f, since g, the second derivative of g, is equal to the first derivative of f, would have to be increasing here. So we'd go look at our graph and figure out where f is increasing. Looking at the slope of f, it's only increasing from -1 to 0. So that's where it's going to be concave up, from -1 to 0. All right, so now we want to look and see, well, what values of x will g have an inflection point at? Now remember, points of inflection are going to be where the second derivative has a sign change. Now, since we're not actually working with the second derivative equation, everything's in terms of f, so we relate the second derivative of g back to f. Well, the second derivative hinges on if f is increasing or decreasing, so we'll have a sign change in our second derivative where f changes from being an increasing to decreasing function, or where it does the exact opposite, where it goes from decreasing to increasing. So we go look at our graph. F here changes from being decreasing to increasing at x is equal to -1. And it also changes from increasing to decreasing at this point here at x is equal to 0. So we have 2 points of inflection. We have a point of inflection at x is equal to -1 and at x is equal to 0. All right, so now we want to put all this together to make the graph. So I start by using all of the values in our table that we got for y values of g, and we place them onto our graph. And then now what we want to do is we want to take all of the behaviors that we've gotten from doing this information, and we want to put this into the graph to get the correct characteristics. So we're going to start with going from, let's go from -3 to -1. Now this function is continuous everywhere, so that we have plotted. So we're looking in from -3 to -2, we got to increase. That makes sense to get up to there. But also from -3 to -1, we have to be concave down. So I'm going to change from being increasing to decreasing at -2, but I got to be concave down the whole time. So I'm going to do something like this. And now we work our way to the next piece we figure out, well, what's going on here at -1 and what's going on here at 0. Well, at -1, we have to be a point of inflection. So we are going to concave down, and then we must be going concave up from -1 to 0 here. So we're going to be concave up. And however, we also have to be decreasing the whole time because we've got to be decreasing from -2 to 3. So this whole portion we got to be decreasing, but I got to make myself be concave up inside of here. So I'm going to do that concaved up. And then at x is equal to 0 here, we're going to be back concave down and decreasing. So I'm going to be concave down and decreasing here the rest of the way. So I get that kind of behavior through there.